А, все, порядок. Да, все, порядок.
Все, никаких проблем нет.
А здесь его?
А здесь создать доску возможно.
So I sincerely hope that this week we'll finish combinatorial preparations and start the hardware of GGLF of FQ. We are almost there. So last time, what did we achieve? Oops. We introduced scalar product. On lambda t with values in maybe u of t, but in reality it will take values in polynomials within the coefficients, but it was characterized by the properties that the usual power sum functions were almost orthogonal. And also an equivalent property was that Q lambda and M mu is equal to delta lambda mu, and the same as M mu and Q lambda. So it's symmetric. Well, it's also symmetric from this point of view. Okay, and then we had the last corollary that the transition matrix from monomial functions to small q functions was symmetric. And I guess this was the end. Now today we continue with proposition 8, stating that the product of y minus t x I y j over y minus x I y j is equal to the sum of whole Littlewood polynomials times renormalized whole Littlewood polynomials, and the renormalization was given by a certain B function. Last time we proved some important characterization of orthogonality, and in terms of this expansion of this product, so it means that the scalar product of p lambda of x t and q mu of x t is delta lambda. Okay, so we are now we are proving the position. And we introduce matrices A, the transition matrix from big renormalized Q polynomials to small Q polynomials. B, transition matrix from the renormalized whole two polynomials to the monomial functions. And finally C, the product of them, the transition matrix from monomial functions to the small q functions. And well, we had some corollary. We proved some proposition maybe a week ago that the renormalized Hollywood functions were obtained from small q by certain composition of raising operators, and the corollary was that the transition matrix was upper triangular, strictly upper triangular. Strictly lower triangular, sorry. Also, we know that B is upper triangular. And this is so because B inverse is the product of a transition matrix from whole little wood to normalized, renormalized whole little wood times the transition matrix from Schur to whole little wood times the transition matrix from monomial to Schur. Okay, and now we know that this one is diagonal, since Q are just renormalized B, and this one is strictly upper triangular. This we proved also some time ago from Schur to their deformations, whole little wood functions, and finally from monomial to Schur is also strictly upper triangular. Okay, so we know about A and B inverse. What else do we know? We know that the matrix C, which is A, B inverse, is symmetric. Okay, And this means that B inverse transposed times A transposed is equal to A B inverse, or equivalently A transposed B is equal to B transposed A. Let's call it D. But now this guy is upper triangular. But this guy is lower triangular. And hence this one is diagonal. That's why it's called D. Okay. Moreover, this D is equal to the diagonal of B, since A is strictly low triangular, so the diagonal of A is all ones. Okay. So we conclude that D is the transition matrix from renormalized whole little wood polynomials to whole little wood polynomials, and hence D lambda lambda diagonal elements are just equal to B lambda of T inverse.
I'm sorry, why
Yes.
D is MPQ?
Because of this, so A is from Q to small q. B supposed is Yes. Yes.
It's because D is the diagonal of B.
Yes.
And you just need to look at the decomposition of B inverse, which completed the corner. B
but
inverse is a
B is from
Yeah, that's right.
M to Q.
yes.
Look
Just
here.
look at the corner. You can just written the decomposition of B inverse. You can invert it to get the decomposition of B into two upper triangular, one diagonal. This diagonal one is just the
Just this.
Yes, yes, yes.
Right. Right.
Strictly, and the diagonal.
Okay. Okay. Thank you. Okay. So the sum of Q small lambda and small lambda of Y is the sum of lambda, mu, and nu, A lambda nu. Yeah, maybe I shouldn't have. Yeah, like this. A lambda mu, B lambda mu, Q mu of xt, Q mu of xt, and this is equal to the sum over mu, B mu of t inverse, Q capital mu xt, Q mu yt, and this is what we wanted to have, P mu times Q. Okay. Now, well, maybe I should have said this before, but anyway, this scalar product as t specializes to 0 becomes the usual scalar product on lambda, well, say, as z lambda of t equals 0 is just z lambda, and also p lambda at t equals 0 becomes s lambda. And so all the definitions of the scalar product they degenerate to the standard ones. Say as also BP lambda at t equals 0 also becomes 1. So P lambda and Q lambda are the same as just the Schur functions, and they do form orthonormal bases. Okay. Now, maybe let us prove the following lemma. I mean, we are almost done. Now we'll study the certain a few more transition matrices. Say the transition matrix from P lambda to S lambda consists of Kostka polynomials, so-called, and we'll need two more transition matrices consisting of so-called green functions. They will enter our computation of characters. They will be the key part of this computation. But in order to do this, we will need some classical lemma. I mean, it is a maybe known fact from standard symmetric functions, but since we essentially omitted the study of classical symmetric functions, well, let me prove this lemma. So it's somehow out of place here, but we'll use it in 10 minutes. So the transition matrix from complete functions to Schur functions is the product of raising operators 1 minus r ij. I mean, we'll prove to something similar, that the transition matrix from small q polynomials to big Q renormalized Hollywood polynomials was something like this, only had also denominator with t. But the numerator appears here, and it will be important. So we use the Frobenius formula. sure function S lambda is the sum over all permutations. I mean, if the number of variables is n, epsilon of w, complete functions h lambda plus delta minus w delta, and delta is as always n so on, and minus 2, so on, 0 of length n. Okay, so this will not prove, this is very well known. And what is it, by the way? Pardon me?
The reformulation of Jacobi-Trudi formula?
Yeah. Yes, certainly. It's all this, but somehow, well, as lambdas, they are characters of irreducible representations of GLN. Yeah, one of the meanings, so physical meaning or whatever, representative theoretic meaning is this character. And then at the level of characters, what is the meaning of this formula? Doesn't it somehow remind you something? These are just science. So it's alternating sum of such guys.
Delta is one half of the sum of positive roots. Okay.
You mean this delta? Yes, so certainly delta is what is usually called a rho in the representation theory, yes.
So lambda plus delta minus w, delta is a dot product.
Yes, and so
It's y.
like the wildcard formula in constant form, so to say. So it is, well, have you heard about BGG resolution? Yeah? No? No? Bernstein-Gelfand resolution. And for Verma modules, category O. But then some of this is exactly the point why Bernstein-Gelfand started studying category O. So you have so lambda the dominant weight, let's say Gn, and you have V lambda, the corresponding irreducible representation, finite dimensional. But then certainly it's well, the unique finite dimensional quotient of the corresponding Verma module, right? But then this projection has a certain kernel, and you know what are the generators of this kernel? Yeah. Namely, there is the sum over all simple reflections, and here you will have m si dot lambda. Notes that there's a notion of dot action. This is the dot action. Yeah, and yeah, for example, for GL2, yeah, this will be Vn. There will be the Verma module with highest weight n, and then the kernel will be just a unique Verma module with which highest weight. For example, if it's 0, then it's also 0, and what is here? Minus 2, yeah. And in general, it's negative 2 minus n. And it is an exact sequence, so this is an embedding. But for higher rank, this is not an embedding. this thing also has a kernel. In general, there will be the sum over the length of W equal I. Well, I is not a good idea. Equal R maybe. M W dot lambda. Okay, and this will be an exact sequence. So at the very end, there will be M W naught dot lambda, and then 0. So this is the exact sequence. Bernstein, Gelfand, Sergei Gelfand, and another Gelfand, Israel Gelfand, resolution. So it's a resolution by Verma modules, the modules where the negative part, lower triangular part of GLN acts freely. Okay, and then from the existence of this resolution, the character of V lambda is just the alternating sum of characters of those Verma modules, and you get this formula. Okay. So now let's do a formal trick. So consider a ring just of Laurent polynomials of some extra variables that has nothing to do with anything else so far. Okay. And then in this ring, we will have the sum over all permutations, z to the power lambda plus delta minus w delta, and this will be equal to z to the power lambda plus delta times a negative delta. That's just van der Motte determinant. Okay, this will be equal to z to the power lambda plus delta, the product over I less than j, z I inverse minus zj inverse. Okay, and this will be equal to the product over I less than j, 1 minus zi zj inverse times z to the power lambda, and this is equal to the product over I less than j of raising operators applied to z lambda. Meaning that R applied to the lambda is z to the power R lambda, raising operator R. And Rij, it raises i's entry and by 1 and lowers j entry by 1. Okay, so now I apply a z linear operator phi from our Laurent polynomial ring. to the image symmetric functions in n variables, namely z to the power alpha goes to the complete function h alpha for any how was it called? Sort of composition, but composition with negative, but possibly with negative entries. And get what we want. So this was our lemma. Maybe I'd rather move this. If you don't need it anymore, it's just some proof, it doesn't matter. Yes. Okay. Now. Recall that the Kostka matrix K is the transition matrix from monomial functions to the Schur functions, and since M lambda and H lambda form the dual basis, while S lambda is orthonormal, we get that the transition matrix from complete symmetric functions to Schur functions is the inverse transposed Kostka matrix. Okay. And now we define the deformation of this, the Kostka polynomial matrix, K of T, is the transition matrix from whole polynomials to the Schur functions. And we already proved and used that this is strictly upper triangle. So K 0 equals K. Okay, so for any T and U, the product, so the transition matrix from one set of polynomials to another one is certainly the ratio of these two Kostka matrices. Okay, and sorry, this was wrong. K of 0 is identity. Sorry. Is identity, and K of 1 is K. Just because P of P of 0 is M, and P of 1 is S. Okay.
I'm sorry,
Yes.
is it not the other way around?
Yes.
Before we had P when T equal 1 is M, and when equal 0 is S.
Right.
Yes.
Right. Sorry. S. M. So it's
Yes.
the other way around. Sorry. Huh?
K0 is identity because it's just transition matrix from the basis to the same basis.
Yes. And this is
Yes.
okay. Fine. So we'll need this lemma now. Have a look at this. Okay. So the transition matrix from small to big Q is the transition matrix from monomial to whole Littlewood transposed inverse. That's because they are dual bases. Q is dual to big P, small q is dual to small m. And this is equal to the Kostka matrix of T inverse K transposed inverse, and this is equal to K of T transposed K transposed inverse. So we know from the lemma that the K transposed inverse is the transition matrix from the full to sure and is equal to the product of raising operators. And hence we obtain proposition 10, probably. No? Or maybe I screwed up the numbering, but that would be 10. Did I give a previous number of proposition? No?
Sorry, just a little question.
Yes.
Maybe very stupid, but how do you define H lambda plus delta minus omega?
Minus W delta, yes.
Because it might be negative.
Then zero, certainly.
And
Then zero.
it may be a composition and not a partition. Or you mean reordered?
No, because delta is strictly decreasing.
But
When you
Is it define h n is 0 when n less than 0, when n negative, and so the whole product will be negative if one of them is negative.
yeah.
If it's not positive.
if it's
But if it's you ask if it's positive, but not ordered, yeah, it's composition.
yes.
Just reorder and
Oh, it doesn't matter.
yeah. So
It's 9 should be.
huh?
I think it should be 9.
Should be 9. This should be 9. Okay. So the transposed Kostka matrix of T is the product over I less than J, 1 minus T Rij inverse. Just because we had this transition matrix between small and big Q, it was this times that. And now just multiply by, or maybe divide by that, and get with the get left with the denominator. So it follows from proposition 4. Okay. Now, maybe I will not prove this, but it is the known fact that actually those Kostka polynomials just, well, the Kostka numbers are all non-negative integers. This we do know. Yeah, there are multiplicities of irreducible modules over symmetric group in the induced modules. And they are the sum of coefficients of Kostka polynomials. Now it turns out that the coefficients of Kostka polynomials also are all non-negative integers. And what is also known that the degree of k lambda mu is n of mu minus n of lambda. Okay, and we will also need at some point the renormalized Kostka polynomials of q, which is q to the power n of mu, k lambda mu of q inverse. Okay, so this is equal to q to the power n of lambda plus higher order. Oops. Terms. Okay. And well, this fact has some purely combinatorial proof, namely the Kostka number is the number of semi-standard tableau of the given shape and weight. But then you introduce certain combinatorial statistics on such Young tableau and number the Young tableau of given shape and weight of this extra statistics. And this gives you coefficients of Kostka polynomials. But they also have some geometric meaning, which is more appealing to me. So maybe I should say that there is a combinatorial expression for coefficients of k lambda mu of t, and it is due. Well, again, I forgot what to do here.
Top middle green cross.
Top middle green cross. Thank you. So it's due to plus but then there are also is a geometric meaning. Of these coefficients. Well, it uses some measure of singularities of nilpotent classes. So we have lambda dominates mu, and so we have nilpotent orbits. And if you close it, the closure will contain the orbit mu, just German types. Okay, this all happens in the nilpotent cone of GLN. Now there is a notion of Goretzky-McPherson sheaves. So there's some constructible. Do you know sheaves? Sheaves? The usual singular cohomology is cohomology with coefficients in the constant constructible sheaf. But if your variety is singular, then the usual cohomology does not satisfy the Poincare duality, even if your variety is compact. These are not compact, but never mind. And there is some cohomology theory which does satisfy Poincare duality, but this cohomology with coefficients not in constant sheaf but in certain Goretzky-McPherson sheaf, so the Poincare duality holds true for compact varieties. These are not compact, but the point is that this duality has some local nature. So you always, for any variety, you have this Goretzky-McPherson sheaf. If your variety is compact, then you can take the hypercohomology with coefficients in this Goretzky-McPherson sheaf, and it will have duality. But some of the Goretzky-McPherson sheaf is more basic. But now you take the dimensions of Stokes of IC sheaf of the orbit closure lambda in degrees. Somehow all the orbits have even dimension. They are symplectic leaves of Lie, constant Kirillov, Suryo, Poisson structure on the Lie algebra. So they are even dimensional, and these guys will also live in even degrees. So in degrees 2i, and t to the power n of mu minus n of lambda times cost polynomial of t inverse will be the sum of t to the power I, the dimension of Goretzky-McPherson sheaf Stokes in degree 2i. At the orbit. Okay, so this Goretzky-McPherson sheaf will live in degree n of lambda at O lambda, but then as you go to the boundary to some orbits in the closure of O lambda, you will get more and more Stokes in higher degrees, and they will be counted by this cost polynomial. Okay, so from this point of view, it's absolutely apparent that the coefficients are positive integers. They're just dimensions of something. Okay. Also, maybe I should say that k, well, it is known that k lambda mu of 1 is just k lambda mu, the usual cost number. It is the weight multiplicity of weight mu in this module over GLN when the length of lambda is well, less or equal to n. Okay. So you see, maybe I should call this gel maybe M. M. So these are different things, and it's just a miracle that the two things coincide. So one is from the point of view of orbits in GLN, where n is the size of partition. On the other hand, you can ignore the size; it can be arbitrarily big. You only are interested in the length of your partition. Then you can view it as the highest weight of GLN, yes, where m is the length, or more, because I'm extended by zeros. And then you have an absolutely different interpretation, which happens to be the same number. That's the weight multiplicity in the representation of GLN. Okay, and now k lambda mu of t is certain t analog, and again this can be, well, this counts the degrees in the Stokes of Gaius Macpherson sheaves in the affine Grassmannian of GLM. Okay. And so from this point of view, those Kostka polynomials make sense for arbitrary semi-simple or reductive Lie group, for GLN or SON or SPN or E8 or whatever. Okay, so you see that there are two possible generalizations of those Kostka polynomials matrix to other types or other things. You can either consider the Stokes of Gaius Macpherson sheaves in the nilpotent orbits of arbitrary groups like G2, F4, whatever, or consider the Stokes of IC Gaius Macpherson sheaves in the affine Grassmannian of arbitrary groups. And for GLN, for type A, they happen to coincide. But in other types, they diverge. These are two different theories. One is T or Q analog of weight multiplicities in terms of affine Grassmannians, and it works fine. But another one in terms of nilpotent orbits is more relevant to what we are doing now. So if we were studying the characters of affine groups of Lie type, like symplectic or orthogonal over affine fields, we would need to compute these things for other groups. And it is also possible, it's called Lustig-Shorty algorithm. It also gives things, but these things are called green functions. And now we turn to those green functions. Okay. So we and Green is the Sandy Green who computed the characters of GLN over FQ. So first we introduce a matrix X of t, and this is the transition matrix from the whole little with polynomials to the power sum functions. So that p sub rho of x is equal to the sum over lambda x rho lambda of t p lambda of x t. So we know that p lambda of x 0 is the show function, and hence the specialization of this X matrix at 0 is just the character table of the symmetric group. The characters are numbered by partitions. The cycle types are also numbered by this is this chi lambda of W rho. So well, this is cycle type. And this is the character of the symmetric group S cap. Okay, so I was always claiming that some unipotent representations of GLN over finite field are also numbered by partitions, and we may compute the value of their characters at the unipotent elements in GLN over FQ, which are also numbered by partitions. And this is sort of deformation Q or T analog of the usual characters of symmetric group. Okay, and indeed this matrix will appear in our character calculation. That's why we are introducing it now. The orthogonality relations of propositions 6 and 8, but now I'm afraid I screwed up my numbering. These were the decompositions of the product of one.
If PQ, grade P and grade Q, it was 8. Proposition 8.
Okay, so let me write down what I mean. Sorry. 1 minus t xi yj over 1 minus xi yj. On the other hand, it was the sum of z lambda of t inverse p lambda of x p lambda of y, and this was number 6, I hope.
Yes.
On the other hand, it was the sum of Hollywood polynomials times renormalized Hollywood polynomials, and this I tend to call 8, but
Yes.
this is true. Fine. Okay. So from this, it follows that the sum over all partitions of size n, z rho of t inverse, p sigma of x, p sigma of y, is the sum over all partitions of size n, lambda, b lambda of t times p lambda of xt, p lambda of y. And now we can express the power sums via Hollywood polynomials. We get that if you take the X matrix transposed times the inverse times X of t. I mean, this is just the diagonal matrices. Is again the diagonal matrix B of t, and this means that X matrix times B of t inverse X of t transposed is equal to Z of t. And this is equivalent to the sum over partition 0 of size n, 0 of t inverse x rho lambda of t x rho mu of t equals delta lambda mu beta lambda of t. And this is the first orthogonality relation. But also we can rewrite it in the form that the sum of partitions lambda of size n b lambda of t inverse x rho lambda of t x sigma lambda of t equals delta rho sigma 0 of t. So when we specialize t to 0, these are they become the orthogonality relations of irreducible characters of the symmetric group. Okay. Now, well, we need this notion that we're considering the matrix transition from transition matrix from Hollywood polynomials to power sums, right? That deforms the character matrix of the symmetric group. Okay. Again, expressing Hollywood polynomials via the power sums, we get the renormalized Hollywood polynomial of xt equals the sum of rho z rho of t inverse x rho lambda t p rho of x Yeah, this is because x of t inverse is b of t inverse x of t transposed z of t inverse. So we have this. So we also know that the transition matrix from Littlewood to Schur is equal to the product of transition matrix from Schur to power sums inverse times the transition matrix from Littlewood to power sums. Okay, and hence the Kostka matrix K of t is the ratio x of 0 inverse x of t. So x of t is x of 0 times k of t, Kostka matrix. That is x rho mu of t is equal to the sum of lambda of size n, the character value lambda at the cycle type rho, k lambda mu of t, the Kostka matrix. So we discussed that the degree of the Kostka polynomial is equal to n of lambda minus n of mu. N of mu minus n of lambda. Sorry, that's the opposite. So at least it is less than or equal to n of mu. Okay, and the leading coefficient is 1. And this implies that the leading term in here, in this sum, is the character value for the trivial representation at any element times k and mu of t, and this is just t to the power n of mu. So we see that the degree of x rho mu of t is exactly n of mu, and the leading coefficient is 1. And knowing all this, we can define the green functions finally. Maybe let me define them here. The green functions. Q rho lambda of q is q to the power n of lambda x rho lambda of q inverse. So this is the renormalization we used many times by now. Okay, and okay, let's just shift slightly. Oops, like this, and I rewrite those orthogonality relations. I just rewrite those in terms of green functions. So the first will be the sum over coefficients rho of size n, y rho of q inverse, q rho lambda of q, q rho mu of q will be delta lambda mu k lambda of q, and I will momentarily explain what is y and what is a. But a already had it. So this is equivalent to the first one, and the second one is the sum over partitions lambda of size n, a lambda of q inverse, q rho lambda of q times q sigma lambda of q equals delta rho sigma y rho of q. Okay. So here y rho of q is q to minus n, the size of rho, 0 of q inverse, and a lambda we already studied a couple of weeks ago, or maybe 3 weeks ago. So a lambda of q is the order of automorphism group, automorphism group of n lambda, the finite O module of type lambda. Yeah? So in fact it is equal to q to the power n, the size of lambda, plus 2 n of lambda, times b lambda of q inverse. By the way, from this point of view, the automorphism of this finite type module, it is just the order of centralizer, the centralizer in GL and FQ of a unipotent element of Jordan type lambda. So remember, Z lambda was the order of centralizer in symmetry group of some element of cycle type lambda, right? And this is sort of its QQ analog for GL. Okay. So finally, the equality x rho mu of t equals the sum over lambda character value at the element of cycle type rho, the Kostka matrix becomes, in terms of green functions, Q rho mu of Q is equal to the sum over lambda, the character value of the cycle type rho over the renormalized Kostka matrix. Well, we introduced it before, but anyway, this renormalized Kostka matrix is Q to the power n of mu times the Kostka matrix of Q inverse. Okay, so that's what we will need, and on Friday we will start. The study of characters of GLN. So congratulations. But now I have to stop. But on Friday, I will say a few words about the geometric meaning of these green functions. So they also have a similar interpretation as a sort of dimensions of cohomology of something. Not quite. So the something will be so-called Springer fibers. So you consider the flags compatible with a fixed nilpotent or unipotent element, but then they're called Springer fibers because Springer defined the action of the Weil group, the symmetric group, on these things, and so we can decompose those cohomology in isotypic components under the action of symmetric group, and the dimensions of those isotypic components will be given by the green functions. I mean, the coefficients in Q of those green functions will be the dimensions of isotypic components for a particular cohomology degree. But I will say this in more detail on Friday, and then we will turn to the study of characters. But still, it will take us the whole April, till the end of April, to compute the characters. At least now, all the combinatorial preparations are all over. But the common kinds are not disputed.
Ой, наверное, можно остановить все.
Трансляция не была начата, что ли? Да, трансляция не была начата? Ужас. Но во время записи нужно закончить или что?
Вот так и все. Так, всем так
Ничего не работает.
就是出版社，或者是现在目前。
Или, может быть, наоборот, запись не была начата, а трансляция была? Нет. А? Запись идет, а трансляция? А запись не идет, да? То есть, значит, трансляция уже закончилась. Да. То есть, наша запись все есть? А, все есть.